Good morning everyone. We are into the week number 5 where our topic of discussion is real cycles for reciprocating engines. In the previous week we talked about the gas power cycles or air standard cycles, which of course such cycles can be devised or conceptualized both for reciprocating and rotary engines, but we primarily focused on the reciprocating engines, or to be more precise, automobile devices or cycles suitable for automobile engines. The cycles that we have discussed, among them the Carnot cycle or Ericsson cycles etc., can be conceptualized for both closed and open systems and also for both rotary and reciprocating kind of applications. But the two cycles which were primary focus of our discussion, that is the Otto and diesel cycles, have their application exclusively in the field of reciprocating engines, and therefore we can safely say that in the previous week we have talked about the ideal cycle suitable for reciprocating engines. Now we have seen that the Otto cycle, which is a cycle suitable for SI engines or spark ignition engines, that conceptualizes or visualizes the combustion process in the form of constant volume heat addition, whereas the diesel cycle, which is the ideal cycle for compression ignition engine or diesel engines, that visualizes combustion as a constant pressure heat addition process. That particular heat addition process is the only difference between the schematic representation of both these cycles, that is one with heat addition at constant volume, other heat addition at constant pressure, and accordingly we have done their analysis. We have drawn cycle diagrams on PV and TS planes to see the or to directly compare their nature. We have developed expressions for their efficiencies, work output and other performance parameters, and we have compared them in terms of various parameters. And from there what has evolved is that the most important parameter governing the engine performance is the compression ratio. Generally, with the increase in compression ratio, efficiency of both Otto and diesel cycle increases quite sharply. Of course, that settles down after a bit, but in general with increase in compression ratio it increases, and therefore it is always logical to have higher compression ratio as much as we can, considering the practical limit. Practical limit can be the self ignition temperature for Otto cycle and the practicable space and weight constraint corresponding to the diesel cycle. But as we have mentioned there also, that these cycles are only idealization, that is they provide some kind of upper limit for the operation of those systems. But there are several kinds of practical losses that is possible in those cycles, which reduces the actual output from the cycles and therefore can significantly affect the thermal efficiencies. It is very much possible that suppose I give you one SI engine, and using the performance parameters of that you do an analysis assuming an ideal Otto cycle, and you are finding the corresponding thermal efficiency to be around 70%. However, if we run the actual engine during an experimental condition, you are getting only an efficiency about 30 to 35%. So, there is a huge difference in the theoretical prediction and practically obtained values. So, while the ideal cycle set up some kind of upper limit of operation, but if we are looking to get a realistic prediction about their performance, or if we are looking to design such an engine, then those cycles can give you far off results, and therefore it is required to take into consideration all the practical losses that can be present in the engine operation, so that we can get a more realistic estimation about the performance, and that is what we are going to focus in this particular week. Of course, we are going to talk about the cycles, but we shall be talking more about the different kind of losses and other effects that can be present in the cycle, and accordingly how we can incorporate them to get a more realistic estimation about the cycle performance. So, we are going to talk about the real cycles or factors affecting the performance of the ideal cycle in case of reciprocating engines, primarily the Otto and diesel cycle. So, these are some diagrams which I have shown in the previous week itself. This is a standard reciprocating engine where we know that the piston reciprocates within the cylinder. generally the topmost position is referred as the top dead center and the bottommost position refers to the bottom dead center. So, this is the top dead center position, this is the bottom dead center position, and the distance between these two dead centers is called the stroke volume or displacement volume. The stroke volume is probably the first parameter that is always specified in terms of any engine specification. Like whenever you are talking about say a two wheeler, we talk about 150 cc, 125 cc, or for very heavy two wheelers we talk about 220 cc. This cc is nothing but the stroke volume or displacement volume. Similarly, for smaller cars we talk about 1000 cc engines. For sedans we can talk about 1.4 liter, 1.5 liter engines, more than 2 liter engines for SUVs. These are all stroke volume, nothing else. The volume left on top of the top dead center is the clearance volume. Stroke volume and clearance volume together gives you the total volume of the cylinder, and the ratio of total volume to the clearance volume is the compression ratio, which we have already identified as the most important parameter even in case of ideal cycles, and the same is true for real engines as well. We have the crankshaft here and the crank mechanism. The crankshaft rotates and the corresponding rotary mechanism is converted to the reciprocating motion of the piston by the crank assembly or crank mechanism. 180-degree rotation of the crankshaft corresponds to one complete stroke of the piston. And when the piston is operating, this is the situation that we generally get. This animation I tried to show in the previous week itself, but somehow it malfunctioned. Just look at just this point it starts, this is the suction, now it is compression, this is the power stroke, and now it is the exhaust. In suction, look how the inlet valve is opening, now both the valves were closed during compression and exhaust expansion, and now it is opening again during the exhaust stroke. If I run it again, so this is compression, this is expansion, and now exhaust valve is open to have the exhaust stroke. As soon as the exhaust valve closes, the inlet valve opens again to facilitate the inlet or suction process. So, this way cycle keeps on operating. Generally it operates at a very high speed. It is very common to have cycles operating at something like 3000 rpm. 3000 rpm means we are talking about 3000 full revolution of the crankshaft in 1 minute. So, 3000 revolutions per minute is equal to 3000 by 60 revolutions per second. So, that means we are talking about 50 revolutions per second. That means in 1 second the crankshaft is having 50 revolution, and if we are talking about a 4-stroke engine, we know that 2 revolutions of the crankshaft or 2 full rotation of the crankshaft corresponds to 4 stroke, that is 1 full cycle. So, 50 revolutions per second leads to 50 by 2, that is 25 cycles per second. So, that is a very high speed that we are talking about, and this is generally the way all 4-stroke engines work. This is the ideal cycle, again a slide repeated from the previous week's work. This is the actual operation where we have the compression stroke to start with, then we have the power stroke during which the piston is moving down from the TDC to BDC following a spark which is produced here. There is a 4-stroke spark ignition engine. Then we have the finally exhaust stroke. During exhaust stroke the exhaust valve is open, and at the end of the exhaust stroke, as soon as all the exhaust gases have gone out, we have the suction stroke starting again, during which the piston is moving down, making more space for the new fuel air mixture to come in. And this is the corresponding representation on a PV plane. However, this is the actual cycle, and this we have conceptualized in the form of an ideal cycle, the Otto cycle, just like this, where we have assumed several air standard assumptions, and following which we get this representation. In the Otto cycle, we have 2 isentropic processes and 2 constant volume processes. The heat addition is at constant volume, similarly heat reaction is also at constant volume. In between we have an isentropic compression process and an isentropic expansion process. So, this isentropic compression process is a representative of this compression stroke. This isentropic expansion process is the representative of this power or expansion stroke. The spark which is happening here, that is being conceptualized in the form of this constant volume heat addition, and the exhaust and the inlet process together has been coupled into this one constant volume heat rejection process. This is as per the air standard assumption. This is a corresponding representation on the TS plane, it is generally ideally suited to represent each of such cycles on both PV and TS plane, because area enclosed by the diagram on the PV plane is a direct representation of the total work done, whereas the area enclosed by the cycle on TS plane is a direct representation of the total heat interaction or net heat supplied to the system. And as we know that as per the first law of thermodynamics, for a closed system undergoing a cycle, we know that the cyclic integral of del Q is equal to cyclic integral of del W, from where we can easily say that the net heat supplied to the system has to be equal to net work output that we have obtained from the system. So, any of the diagram theoretically is sufficient to provide you the performance parameters in the form of work output or efficiency, but generally it is logical to represent both, so that we also get ideas about the maximum pressure, temperatures, etc., for the cycle. Now, this is an ideal cycle, the Otto cycle. Similarly, we can also draw the diesel cycle, as we have already discussed in the previous week. Now, let us just quickly take a look at the air standard assumptions using which we have actually plotted this ideal cycle. So, this is the first air standard assumption. If you remember, I am sure that you remember the air standard assumptions. I am writing the same assumptions here. It is a copy of the same slide, but I have reordered those assumptions to suit some requirement. So, one assumption was, the first assumption, that the working medium is air, and we are assuming it to be a closed system, so that we can assume the same quantity of air is continuously circulating within a closed loop. And we are also assuming that there is no inlet and exhaust process. These two processes together are replaced by a heat reaction process, generally a constant volume heat reaction in case of both Otto and diesel cycles, or even in case of dual cycles, but that is different in case of the Stirling and Ericsson cycles, because they generally have heat interactions in the form of isothermal processes. So, in all the cycles that we have studied, starting from Carnot cycle up to Ericsson cycle, in all those cases we are assuming that there are no inlet process and exhaust process, rather those two has been clubbed into a single heat reaction process, which is at constant volume in Otto, diesel and dual combustion cycle, whereas that is isothermal in case of Carnot, Stirling and Ericsson cycles. So, the objective of this heat reaction process is to take the system back to the initial state, means to take the system back to the state at the point of commencement of the compression process. So, these two are the idealizations, but what are the things that we are losing because of this? What are the practical effect or practical factors that actually do not obey this particular thing during real operation? One thing that we are neglecting is the fluctuations during the inlet and exhaust processes. As the fuel air mixture goes in during the inlet process, the pressure inside the system that keeps on fluctuating. In fact, if you just think about the valve, generally outside you have atmospheric pressure or slightly higher than atmospheric pressure, whereas in the inside the cylinder, as the piston starts to go down during the inlet process, the pressure falls below atmospheric, thereby creating a slight vacuum, so that the fuel air mixture can flow easily into the cylinder. But as soon as it starts flowing into this, the pressure inside the cylinder starts to increase, and thereby causing some kind of fluctuations to the valve. The same is applicable to during the exhaust process as well. So, both pressure and temperature that keeps on fluctuating may not be by a very significant margin, but that is very much possible, which can lead to certain issues related to the design of the valves. A bigger problem that we are or bigger issue that we are completely eliminating is the actual composition of cylinder gases. We are assuming the working medium to be air, and it continues to be air during all the processes, all the 4 processes in the ideal cycle. But if you think about the practical cycle, for an SI engine operation, it is the fuel air mixture that you supply. So, during the inlet process and also during the compression process, your working medium is actually a mixture of hydrocarbon fuel and air. So, it is actually a mixture of several gases, like in air we primarily have oxygen and nitrogen, whereas in the fuel we can have several kinds of hydrocarbons, both we can have methanes and similar kind of things, or we can have heavier hydrocarbons as well in the group of ethylene, or even going to even heavier hydrocarbons in the group of benzenes. So, we are completely neglecting this actual composition, and if you think about the post combustion scenario, because of combustion the hydrocarbon gets converted to a mixture of carbon dioxide and water vapor, and in case of incomplete combustion we can also have carbon monoxide, sometimes just something we call soot, that is dry carbon, only some very minute carbon particles. If the fuel contains something like sulfur, we may have oxides of sulfur as well. So, it is again a mixture of gases, and which is actually different from what we had during the inlet and compression processes. This composition of cylinder gases, that has been completely eliminated during the ideal cycle. The variation in the number of molecules over a cycle, that also we are neglecting. The implication of this one we shall be discussing shortly, but as the number of molecules changes, the pressure inside the cylinder also changes proportionately, and number of molecules definitely change because of the chemical reactions. That is also we are neglecting, because we are completely eliminating the chemical reaction, we are considering it to be a fixed mass of air. Then the gas exchange process and the valve timing. Now, what do you mean by gas exchange process? I am just showing you the same diagram for the for the actual cycle. Here some marks are shown. As you can see, though the exhaust process is supposed to start when the piston reaches the bottom dead center somewhere here, the exhaust valve has opened at this particular point only. Similarly, the intake valves opens somewhere here, and the ignition process, the spark, we are supposed to provide the spark once the piston reaches the top dead center somewhere here, but here the spark has been provided a bit below that. This way, these things are called the valve timings, that is exactly when to open the inlet valve and when to close it, when to open the exhaust valve and when to close it, when to provide the spark in case of spark ignition engine, when to spray the fuel in case of CI engines. These timings are very important. We shall be discussing in detail about the valve timing diagram in the next lecture, but for the moment you can take that, though ideally we should open and close all the valves at the dead centers, but practically speaking, considering the finite time requirement for this valves opening and a few other factors, we generally open these valves a bit earlier than where they ideally should open, and also close them a bit later than where they ideally should close. Like the exhaust valve should open at this particular location, but it is opening earlier than this. Similarly, it should close when the piston reaches the top dead center, but sometimes we close it well beyond, maybe somewhere here. So, we are making the opening of the valves earlier than ideally required, and closing them much delayed than ideally required. These things is related to the valve timing, and because of that we can have a gas exchange process. Just focus on this portion. If the inlet valve opens where it is shown, and if the exhaust valve opens at this particular position, then there is a small period of time, small window of time during which both the valves are open. So, the fresh charge that comes in, it is possible for that to get mixed with the exhaust gases, and also some fresh charge may get lost. This is sometimes referred as the gas exchange process. I shall be mentioning about this term a bit more in the next lecture, and this is a kind of loss if we can't control them properly. Similarly, blow down at the end of the exhaust process. To open the valves, generally all these valves in common engines open inward. So, whenever you are trying to open the exhaust valve, we have to open the valve against the pressure of the exhaust, okay, what I am trying to say, that if this is the cylinder and this is your exhaust valve, now when the piston starts to come up in this direction, it is actually forcing the gases against the exhaust valve, and therefore, if we want to open the exhaust valve downward, then we have to open it against this increasing pressure of the exhaust gases. So, that will require some additional amount of work input. To avoid that, what we do, before the piston reaches this bottom dead center position, again I am going back to the diagram, this position, we open the valve somewhere here. So, the piston, as the piston is going down, so there is no additional pressure acting on the valve, on the inner surface of the valve, and so it is easier to open. But as soon as we open the exhaust valve, that is virtually the end of the expansion process. So, this particular thing is referred as the blow down of the exhaust valve blow down, that is again a kind of loss. Those actual losses we shall be talking more in the next lecture. So, these all are losses that is happening because of the first two assumptions, or all these factors we are neglecting. Similarly, we are also assuming air to behave as an ideal gas, but practically we know that it can deviate from the ideal gas behavior under certain temperature conditions. So, that can lead to some loss of information. Also, assuming air to be an ideal gas, we are considering properties like internal energy or enthalpy or specific heat to be function of temperature alone. But certain situations, particularly when we are talking about very high pressure, these properties can significantly vary with the pressure as well. So, that pressure dependence we are taking out of the picture, and therefore, we may again lose some significant information. We are assuming all the processes constituting the cycle to be internally reversible. So, we are neglecting the frictional losses, but friction can always be a very significant factor, and this is a loss we can never avoid. In fact, it can be a significant portion of the difference that can exist between the ideal cycle efficiency and the actual cycle efficiency. In practical engines, in order to avoid or to reduce the friction, we add lubricating oil, and this lubricating oil can get mixed up with the fuel, thereby changing the property of the fuel itself. That contamination effect we are also neglecting. Then we are neglecting the combustion process altogether. The combustion process is replaced by a process allowing heat addition from an external source. Like in case of Otto cycle, we are assuming combustion to take place at constant volume heat addition. In case of diesel cycle, at constant pressure heat addition. Whereas in Stirling and Ericsson cycles, we are assuming this to be isothermal heat addition. And this combustion process, therefore, we are completely eliminating, but that definitely has a significant impact in the actual cycle operation, because like in case of SI engine, we are assuming combustion to be instantaneous. Practically it requires a finite amount of time, and as the combustion progresses, there is a gradual change in the composition of the gases. The dissociation of combustion products, when it goes to very high temperature, the products of combustion can dissociate back to the original products or original reactants, that is called dissociation. That can have significant impact. We shall be talking about this one also shortly. There it is very much possible to have incomplete combustion, particularly in case of CI engines. The hydrocarbons that you are supplying, instead of burning complete to form carbon dioxide, that can form carbon monoxide or some intermediate hydrocarbons, leading to incomplete combustion, and which can affect the thermal efficiency as well. So, unless we properly simulate the combustion process, we can't take care of all these factors. And also heat transfer to the cylinder walls can be a significant factor in reducing the temperature level of the gases. Though we can assume always the cylinder walls to be adiabatic, or rather there is no heat loss to the cylinder walls, but such kind of heat leakage, particularly considering that the temperature inside the cylinder can be in the range of 1500 2000 Kelvin or even higher, such leakages are unavoidable. And finally, we are assuming the specific heat to be constant. That is probably, at least from theoretical point of view, that is probably the biggest source of error that we can encounter, because specific heat are strong functions of temperature, it increases rapidly with increase in temperature. So, because of each of the air standard assumptions, we are losing something, or I should say we are eliminating some of the external factors which leads to the deviation between the actual cycle prediction or actual cycle performance and ideal cycle prediction. And therefore, to add, if not possible for with all, at least some of them can still be taken care of theoretically, and for that we consider something known as the fuel air cycle. Fuel air cycle is a modification of the ideal cycles, where among all the factors that I just listed in the previous slide, not all, but 4 of the factors we are considering or we are adding to the actual cycle. Factor number 1, the actual composition of cylinder gases. In fuel air cycle, I repeat, we are adding these factors to the ideal cycle, which we have already discussed, like the Otto or diesel cycle that we have discussed in the previous week. On those ideal cycles, we are adding 4 factors to have the fuel air cycle, and the first factor is the actual composition of cylinder gases. So, we are going to consider the true composition of the fuel air mixture during the suction and suction and compression stroke of an SI engine, whereas we shall be talking about the mixture of combustion products during after combustion process. In case of CI engine, however, we do not need to consider the mixture, because in CI engine we know that it is only air which is supplied. So, during suction and compression process it is only air. So, there will be no change in case of CI engine or diesel cycle during those two processes. However, during the post combustion processes we need to consider the composition of combustion gases. Then the second factor that we consider is the variation of specificity with temperature. It probably has the most significant effect on cycle performance. Then the effect of dissociation, that is the reversible reaction, or I should say the reverse reaction that can take place at very high temperatures, that will be taken care of. And the variation in the number of molecules, that can also have significant effect, that we shall be seeing shortly. So, these are the 4 factors that we are going to consider in case of fuel air cycles. These are the 4 factors we are going to add on the ideal cycles to get the fuel air cycle. Of course, in fuel air cycles we are still assuming several factors, like no chemical change in fuel or air composition prior to combustion. So, chemical reaction will start only at the point of combustion, but in true engines we may have some pre-combustion reactions with change in temperatures. Those are neglected. We are talking about any change in chemical composition just from the point where combustion is initiated. Then mixture always in chemical equilibrium after combustion. So, that is an important assumption. Then we are assuming no heat exchange between the gases and cylinder walls. We have seen that this can have significant effect. Those kind of leakages, heat leakages we are neglecting, assuming adiabatic walls. Then friction is also neglected. Frictionless compression and expansion processes are assumed. Then negligible fluid motion inside the cylinder. The fluid itself can move inside the cylinder because of such fast motion of the pistons, but that fluid motion corresponding kinetic energy of the fluid, that we are neglecting. We are assuming the fuel to be completely vaporized and perfectly mixed with air during the supply process. So, as we are supplying fuel, we are assuming that the fuel, liquid fuel, that is gasoline, has completely been vaporized, and we have successful in preparing a perfect mixture of this fuel and air, and then only it is supplied to this. Similarly, we are also assuming combustion to be instantaneous, that is at constant volume. Of course, these last 2 points are applicable only for SI engine based cycles, because in CI engine based cycles we have combustion at constant pressure, and also we supply only air. So, these last 2 points are not applicable for CI engines, only for SI engines we have them. So, now let us consider all these 4 factors one after the other. But before that, I would just like to mention that in case of air standard cycles or ideal cycles, which we have discussed there, what is the most important parameter that we have identified that can affect the cycle performance? That is the compression ratio, and that is probably the only factor that we can consider. In case of CI engines, we can add the cutoff ratio to this. The fuel air cycle is the first effort where we are considering the actual composition of gases, that is the nature of the fuel, the nature of fuel air mixture, that comes into play, and therefore, we can analyze the second most important factor in actual engine performance, that is the fuel air ratio. A fuel air ratio is nothing but the mass of fuel divided by mass of air in a mixture, or you can say the mass flow rate of fuel by mass flow rate of air. This mass of fuel and air present in a mixture is represented by this fuel air ratio. Sometimes we talk about the other thing also, that is air fuel ratio. Air fuel ratio is nothing but just the opposite of this, mass of air by mass of fuel present in a mixture. So, after compression ratio, this is probably the second most important factor, but as we are assuming air to be the working medium in case of ideal cycles, so the fuel air mixture or fuel air ratio never comes into consideration in case of ideal cycles, but that we can analyze in this fuel air cycles. And before moving any further, I should mention why we are talking so much about the fuel air cycle, because as we have just mentioned that efficiency predicted by the ideal cycle can be far off from the actual cycle efficiency. However, commonly we have seen that the efficiency of the actual cycle can be quite close to the efficiency predicted by the fuel air cycle. It can well be in the range of 85 to 90% of the efficiency predicted by the fuel air cycle. and therefore, it is very important to have a complete understanding of the fuel air cycle. And of course, we are not going to develop any expression for efficiency here, we shall rather be focusing on identifying the effect of all these 4 factors. And once we know that, once we can properly draw the corresponding modified cycle, then we can calculate the efficiency from there, and that efficiency will be quite close to what we can get in practice. Why there is still some difference? That is because of these assumptions, like we are neglecting any kind of frictional losses, we are neglecting any kind of heat leakage, we are neglecting the chemical non-equilibrium that can be present in the system. All this can have some 10-15% influence, which reduces the actual cycle efficiency even further to the fuel air efficiency. Also, using the fuel air assumption, we can get a correct estimate of the maximum pressure and temperature that can exist in a cycle. The pressure temperature ranges predicted by the ideal cycle again can be far off than real operation, but fuel air cycle gives quite reasonable estimate about the maximum pressure and temperature of the cycles, and also quite reasonable estimate about the role played by different parameters on the cycle performance. And therefore, for design and construction point of view, fuel air cycle probably is more important. But of course, that can't undermine the ideal cycle, because it is the ideal cycle only which allowed us to conceptualize the diagram. We are creating the fuel air cycle by adding these 4 factors on the ideal cycle. So, the ideal cycle comes first, then we are adding these factors to get a more realistic estimation in the form of fuel air cycle, and on that, once we can add the factors like frictions etc., then we get the actual cycle operation. So, the first factor is the actual composition of cylinder gases. The actual composition of fuel air mixture, as we have already mentioned, that can change significantly, and as that changes, corresponding property of the mixture can also change. Like whatever may be the property of air, let us say if we talk about just specific heat, whatever may be the specific heat of air, a mixture of carbon dioxide and water vapor may have a very much different value of the specific heat. So, we need to know the proper composition of the cylinder gases. And in this conjunction, I would like to introduce one term that is known as the stoichiometric ratio or stoichiometric mixture. A stoichiometric mixture refers to a mixture of fuel and air which contains exactly the same amount of air that is required for its complete combustion. I repeat, a stoichiometric mixture refers to a mixture of fuel and air which contains exactly the same amount of air or precisely the same amount of air required to have complete combustion of that quantity of fuel. Like if we consider a simple chemical reaction using methane as the fuel. So, if we have CH4 plus we want to write the chemical reaction. So, we know that we can write it to be 2O2 to get CO2 plus twice H2O. It is a complete chemical reaction. It is complete in all sense or not in all sense, because in practical engine to have the combustion of methane we can't supply pure oxygen, rather we supply air, and air can be visualized to be a combination of oxygen and nitrogen, and generally by volume nitrogen is 3.76 times of oxygen. So, whenever you are supplying any one mole of oxygen, 3.76 moles of nitrogen also comes with that, and therefore, to complete this reaction we also need to have this 3.76 moles of nitrogen on the product side. It is an inert kind of gas, and the way it comes in it just goes out the same way. So, now it is a complete chemical reaction. Then to have complete combustion of 1 mole of methane, how much mole of air we require? We can have a very simple calculation. So, 1 mole of methane, if we take rough values, then we can calculate the mass of 1 mole of methane to be, or let me say 1 kilomole I should write. There is a common SI symbol. So, it is carbon is 12 plus hydrogen is, we take just approximate values 1. So, it is equal to 16 kgs. So, 1 kilomole of methane weighs 16 kgs. Then corresponding air So, we have 2 into 1 mole of oxygen, that is approximately 32. We are taking again approximate number, just neglecting the fractions, plus 3.76 in nitrogen is approximately 28. So, that comes roughly 274.56 kgs. Though, so the stoichiometric air fuel ratio So, from here we get that to have complete combustion of 1 mole of methane, that is about 16 kg of methane, we have to supply 274.56 kg of air, and therefore, corresponding stoichiometric air fuel ratio will be mass of air divided by mass of fuel, and mass of air in this case is 274.56 divided by 16 gives you a number of approximately 17.16. So, the stoichiometric air fuel ratio of methane is approximately 17.16. For practical hydrocarbon fuels, it generally varies in the range of 14 to 16, the stoichiometric air fuel ratios. For practical gasoline or diesel group of fuels, it is in the range of 14 to 16. So, stoichiometric air fuel ratio gives us an idea exactly or I should say the minimum quantity of air required to ensure complete combustion. Truly speaking, in practice, if we provide exactly this amount of air, we may not still have complete combustion, because each combustion depends upon, completeness of combustion depends upon whether each molecule of fuel is able to come in contact with oxygen or not. But theoretically speaking, this exactly this amount of air should ensure complete combustion of methane, and in the product side we shall be having only carbon dioxide and water vapor, no methane left out, no carbon monoxide kind of intermediate product. And another parameter I have to define here, that is called the equivalence ratio. During practical operation, we it is not possible to precisely supply the stoichiometric air fuel ratio. We generally supply additional amount of air or less amount of air, and that factor is measured in terms of this equivalence ratio. Equivalence ratio, commonly denoted by phi, it is defined as the stoichiometric air fuel ratio divided by what actual ratio you are following during the real operation of the engine. So, we are talking about the stoichiometric air fuel ratio to actual air fuel ratio. This ratio we are calling as the equivalence ratio. Like if we talk about, say, a given, if we just go back to this example of methane. So, we are trying to get complete combustion of 16 kg or 1 kilomole of methane, then this one can be written as the stoichiometric air fuel ratio will be this 274.56 divided by 16 divided by actual. So, mass of actual air that you have supplied again divided by 16. So, it reduces to this stoichiometric quantity of air that we have calculated divided by the mass of air actual. I should put the subscript actual that we have to supply. So, or we can so when we are talking about a fixed quantity of fuel, this one can be represented in terms of the corresponding quantity of air. When this phi is less than 1, what does that mean? When phi equal to 1 means what? That is, we are talking about the stoichiometric mixture only. Actual air fuel ratio and stoichiometric air fuel ratio are equal to each other, and we have supplied the stoichiometric quantity of air only. When phi is less than 1, that means we have supplied more amount of air than required for complete combustion, and that mixture is known as a lean mixture. That particular air fuel mixture is known as a lean mixture. Lean means it contains more air than required. We have supplied air more than what is required from stoichiometric consideration. Whereas, when phi is greater than 1, what does that mean? Then we have supplied less amount of air than required. We call that rich mixture. Rich mixture means we have to supply more air, or whatever minimum quantity of air is required, we have not supplied that, we have supplied less, or on in from other point of view, you can say that for a given quantity of air, we have supplied more amount of fuel. That is why this lean and rich terms comes in. Now, this composition, when you are talking about this composition of cylinder gases, then this stoichiometric air fuel ratio and the equivalence ratio comes into picture, because they strongly can affect the performance of the cylinder gases. This is one diagram where we have the compression ratio in the horizontal axis and the thermal efficiency on the vertical axis. This is the air standard efficiency. As the compression ratio increases, it increases. Now, look at this actual diagram now. When you are talking about 100%, we are actually talking about the stoichiometric mixture. You can see there is a significant difference between the actual prediction and the air standard prediction, or you can say this difference is the red one corresponds to the ideal cycle, the air standard cycles, and this purple line corresponds to the fuel air cycle working with stoichiometric mixture. And now, as the composition changes, if we make the mixture leaner, that is we add more amount of air, you can see the efficiency has actually increased when you have gone to 120%. Whereas, when you are talking about a richer mixture, it has this equivalence ratio has come down to 80%. Sorry, we are talking about a richer mixture, equivalence ratio is greater than 1 in this case, but mixture is rich, or you can say we have supplied 80% air than required to have a stoichiometric mixture, then we are having a reduction in the efficiency. So, in practical engines, lean mixtures give you better performance. Of course, there is some limit, it does not mean that you can keep on adding more and more air, but generally a leaner mixture, particularly in the range of 120 to 130%, or equivalence ratio in the range of 0.8 to 0.9, we get very high values of efficiency. So, the composition of cylinder gases definitely can affect the performance. To get the theoretical prediction about these values, we can use different combustion charts, or nowadays with digital computers we can easily go for detailed combustion analysis. The next factor, that is the variation in specific heat with temperature. This is something that we can directly represent on the cycles. Specific heats are strong functions of temperature. When you are talking about lower temperatures, say something in the range of 300 to 1500 Kelvin, it is generally Cp follows a relation of A plus B1T, and similarly Cv follows A bar plus B1T. This is generally in the range of 300 to 1500 Kelvin. And what is the relation between these two? So, if we write Cp minus Cv, it will be equal to A minus A bar, and what is the difference between these two? That is R, or the gas constant. So, the difference between Cp and Cv always remains constant, and if as in this case Cp and Cv almost follows a linear relationship over this temperature range, and when you go to higher temperature, then Cp becomes a quadratic function, something in the form of B1T plus B2T square, and similarly Cv can be written as A plus or A bar upon A plus B1T plus B2T square. This is when the temperature is greater than 1500 Kelvin, which is quite common in case of IC engines. So, you can see as the temperature increases, the specific heat keeps on increasing very rapidly. If I can give you one simple example, so if we talk about air, Cp for air at normal atmospheric temperature like 300 Kelvin is about 1.005 kilojoule per kg Kelvin. This is at T equal to 300 Kelvin. Whereas, when we go to T equal to 2000 Kelvin, this one becomes 1.345 kilojoule per kg Kelvin. There is a significant change in the value of the specific heat. Corresponding change in the Cv can also happen. Means the same way Cv, just if we subtract R from there, R for air, the value of Cv can also be obtained, and the change in Cp and Cv is directly reflected in terms of the K. Like if you think about the Otto cycle efficiency, we know that the efficiency is predicted as the ideal thermal efficiency for an Otto cycle is 1 minus 1 by R to the power k minus 1. Now, this R here is a design parameter, because the compression ratio depends on the location of top dead center and bottom dead center. So, for a given engine the compression ratio is fixed, but K is a property of the gas mixture that we are talking about, and K is a ratio of Cp and Cv. So, if we just use this particular relation, so we can write Cp as Cv plus R upon Cv, that is 1 plus R upon Cv. Now, as the temperature increases, we can see that Cv increases, then what will happen to K? As Cv increases, K will decrease, and therefore, it is directly going to affect the thermal efficiency and all other similar calculations. Let us check the standard Otto cycle diagram. This is a standard Otto cycle diagram where we are starting the compression process from point number 1 and following isentropic process we are going to point number 2. Now, we know that T2 is equal to T1 into R to the power k minus 1. Now, as the compression process goes on, the temperature also keeps on increasing, and as the temperature increases, corresponding specific heats change, and as the specific heats change, corresponding K will decrease. Then what will be the effect of this? As the specific heat is changing, then if we modify the diagram, your actual compression line will start deviating from this because of the change in K, because the temperature that is at a particular point being predicted by this relation, that is no longer valid. As temperature is increasing, K is continuously decreasing, and at the end of compression we may reach up at a point somewhere here, this 2 prime. This T2 prime can be significantly lesser than the T2. Remember, the volume is same corresponding to both 2 and 2 prime, because they are talking about both TDC location, but it is only because of the change in specific heat with temperature or corresponding reduction in the value of K with temperature that point 2 has come down to 2 prime. So, this way we have a reduction in the location of point 2 prime. And now, if we talk about the constant volume heat addition, instead of starting from point 2, we are starting from point 2 prime. Now, if you are giving a fixed amount of energy Q in the ideal process, it is equal to Cv into T3 minus T2. In the actual process, what is happening? Already we have down to point 2 prime, Q in remains same, but we are Cv into T3 minus T2 prime. We are already down to point 2 prime, which is at a lower temperature, and during heat addition Cv will increase even further with temperature, thereby causing a further reduction in this location of 3 prime, and the heat addition process may go on and may end up only somewhere here 3 prime. So, 2 prime is the point signifying the end of compression process, and 3 prime will be the end of combustion process. This difference between this 2 and 2 prime has been manifested even further between 3 and 3 prime, because the 3 prime has come lower or has come down from 3 because of the lower positioning of this 2 prime, plus even further reduction in Cv with increase in temperature. During this heat addition process, temperature increases very rapidly, accordingly Cv increases also very rapidly, and if Q in remains constant, then as Cv increases, corresponding temperature rise will be even smaller, which is signified here, and this is a constant volume process. So, as the temperature, final temperature reduces, final pressure also will reduce. Like in ideal situation, you should have P3 upon T3 is equal to P2 upon T2. This is the ideal situation. What we are getting here? Here we are getting P3 prime by T3 prime is equal to P2 prime by T2 prime. As 3 prime and 2 prime all has come to a lower location, so P3 prime also will be lower than actual P3. Similarly, here we shall be having T3 prime lower than theoretical value of T3. So, this is significant modification in the expression of the cycle for this. Now, what about the expansion process? During the expansion process, if the specific heat remains constant, then just we shall be having a line somewhat like okay, let me draw properly. Your line will be something like this, ending up somewhere here to give you the point 4 prime, and 4 prime to 1 is the exhaust process. But actually when this expansion is happening, what is happening to the temperature? As the expansion is happening, temperature is decreasing. Now when temperature is decreasing, Cv also decreases, accordingly K increases. Now as K is increasing, in this case the line will now start moving in the higher direction, because as K is increasing, temperature will increase. This green line, green continuous line that I have drawn from 3 prime to 4 prime, that actually does not take into consideration the change in specific heat. But if we want to consider the change in specific heat with increase in temperature, then your line will be somewhat like this and finishing up somewhere here. So we shall be having a point 4 double prime, which signifies the end of the cycle. So during process 1 to 2, we are having a final temperature, or sorry, during process 1 to 2 we are having a lowering in the temperature level, and so the final temperature at the end of compression, both temperature and pressure are lower than ideal cycle. During constant volume heat addition, again specific heat is changing, because of that the final temperature and pressure at the end of constant volume heat addition is significantly lower compared to the ideal cycle. And similarly the temperature and pressure at the end of expansion is also lower than the ideal cycle prediction. However, that is there is some kind of recovery because of the increase in the temperature, sorry, because of the reduction in temperature and corresponding increase in the value of K. So if we combine all these factors, this is the diagram that we have. Here 1, 2, 3, 4 is the ideal Otto cycle. This dotted yellow line represents the compression process, actual compression process, forcing the point 2 to come down to 2 prime. Then 2 prime to 3 is the actual combustion process. Then you can see there are two lines drawn. The black line does not, the dotted black line does not take into consideration the change in specific heat during expansion, whereas the dotted red line, that is I am talking about this particular line, that takes into consideration the actual cycle or change in specific heat because of the during the expansion process because of the reduction in temperature. So this is not written properly, this should be 4 prime. Here this 4 double prime, this point has been identified neglecting the change in specific heat during expansion. However, 3 prime to 4 prime is the true expansion process, which takes into consideration the reduction in temperature and corresponding increase in K during the expansion process only. So now look at the two diagrams. You have the theoretical work production from this cycle. So W theoretical, or I should write net work output theoretical, or that is predicted by the ideal cycle, is the area 1, 2, 3, 4, 1, whereas the net work output from this fuel air cycle, considering only one effect, of course here everything is drawn considering only the variation in specific heat to temperature, what we are getting here, your corresponding area is, it starts from 1, then goes to 2 prime, then we have 3 prime, then we come down to 4 double prime and then 1. And which area is smaller? Definitely the second area is a bit smaller, particularly the expansion process is starting from a much lower pressure level, which always signifies a lower work output from this. Similarly, the final temperature level is also lower, this 3 prime corresponds to peak pressure and temperature, and as I have mentioned earlier, the peak pressure and temperature predicted by the ideal cycle, which corresponds to this point 3, is quite far off than what is being predicted by this fuel air cycle, considering the effect of specific heat given by this point 3 prime. So this is the effect of the variation in specific heat with temperature. But the question is, why specific heat should vary with temperature? The answer, a rough answer can be given by considering the amount of energy absorbed by the atoms. Specific heat corresponds to the energy absorbed by the molecules, but inside molecules you can have atoms in case of multi-atomic molecules, and a portion of that energy also goes to the atoms. And as the energy level, temperature level increases, molecules keep on vibrating and the atoms inside the molecules also keeps on vibrating and their vibration level keeps on increasing. Therefore, as we move to higher temperature, more and more energy will be required towards this added vibration or enhanced vibration of the atoms. So, more amount of energy will be absorbed by the molecule itself for a given amount of temperature rise. That is what can be a rough explanation about this increase in specific heat for this, and the effect of that you can clearly see from here. Next is the effect of dissociation. Effect of dissociation talks about the reverse chemical reaction that can happen only at very high temperatures. Like we know that C plus O2 leads to CO2, but that is at normal condition. When you go to very high temperature, then CO2 dissociates to form CO plus O2. This happens when the temperature is generally beyond 1000 degree Celsius. Similarly, the water vapor can also break to hydrogen and oxygen when the temperature crosses something like 1300 degree Celsius, and both these reactions are endothermic in nature. That is, when these reactions happen, they will absorb energy from the surrounding for these reactions to happen, and therefore, as the temperature increases, the rate of dissociation keeps on increasing and the corresponding in amount of energy absorbed from the surrounding material, that also keeps on increasing, thereby lowering the temperature of the total system. Accordingly, it can have again significant effect on the system performance. Look at this. During the compression process, generally the temperature level is quite low. At the end of compression, this temperature also significantly lower to cause any kind of dissociation. Dissociation comes into picture during the combustion or heat addition process, and as we move in the higher from point 2 to 3, maybe a point somewhere here, if dissociation starts to get initiated, that will restrict the temperature rise, because whatever heat is being added, that from the surrounding source or the amount of heat produced because of combustion, that will again get absorbed because of this endothermic dissociation reaction, and so the final temperature will get restricted to some 3 prime. So, again the effect of dissociation is to reduce the peak temperature. Remember, here there is no change in the position of this point 2, because dissociation is not associated with compression process, that is primarily associated with this combustion process, and because of this, now your expansion again will have something like this, follow a line to move to a point 4 prime. But the opposite effect, similar to the previous case, we can have the opposite effect here as well. As the temperature starts to come down during the expansion process, again this products of dissociation, that is CO and O2, recombines back to form CO2 there, and that reaction is exothermic. So, some additional energy is produced. So, this line may deviate a bit, and again it will end up at some point 4 prime. But truly speaking, this dissociation products recombination, that generally happens towards the end of the expansion process, and that time the pressure level is too low to have any significant effect on the cycle performance. So, again if we talk about the net work output from the theoretical cycle, that corresponds to the area 1, 2, 3, 4, 1, whereas the net work output predicted by this fuel air cycle, considering the effect of dissociation only, then it will be the area corresponding to 1, 2, both are not changing, 3 has come down to 3 prime, 4 has moved to 4 double prime and 1, and this area definitely significantly smaller. If we hatch this out, your hatched area for the actual fuel air cycle or fuel air cycle, considering the effect of dissociation, is this much, there is still some amount of area left. So, there is significant reduction in the total work output. So, the effect of dissociation is to reduce the total work output and also to reduce the maximum pressure and temperature of the cycle. We can also think about what we mentioned in conjunction with Carnot cycle. In order to increase the thermal efficiency, we need to have the temperature of heat addition to be higher, and as this maximum cycle temperature is reducing, so the mean temperature of heat addition is coming down, thereby lowering the thermal efficiency. the effect of dissociation actually strongest corresponding to the stoichiometric mixture. Here we have plotted the brake power or the power output corresponding to the air fuel ratio, which is in the range of 14 to 16 for common hydrocarbons. So, you can see the effect of dissociation is the strongest for the stoichiometric mixture. This black dotted line means I am talking about this line corresponds to the brake power or power output variation with air fuel ratio, and we get the maximum output corresponding to the stoichiometric mixture, which is given by this vertical dotted line. And because of the presence of dissociation, that is shown by the red line, you can see the effect of dissociation is strongest for the stoichiometric mixture, simply because stoichiometric mixture produces the highest temperature. When you are talking about a lean mixture, means we are moving to this side, less amount of air available. For lean mixture, the total temperature is too high. Sorry, I am talking about a rich mixture. Sorry, I am sorry, I would correct myself. In this direction, air fuel ratio is increasing. So, we are talking about a lean mixture here, and in this lean mixture, air is more, fuel is less. So, the total energy released during combustion is less. So, the maximum temperature that can be produced, that is also less. So, dissociation effect is lesser. Similarly, when air fuel ratio reduces, that is we are moving to the rich mixtures. In this case, fuel is more, but air is less. So, there is more probability of having incomplete combustion. Incomplete combustion means in your combustion product you already having the terms like CO and O2 present, and the presence of these products reduces the rate of dissociation or probability of dissociation. So, again the effect of dissociation is lesser for rich mixtures. So, the dissociation is the strongest corresponding to the stoichiometric mixture. Similarly, we can also see the maximum temperature. This is your maximum temperature, and this thing can be called the degree of richness. Here 0 corresponds to the stoichiometric mixture, and anything greater than this is rich mixture, less than this is the lean mixture. So, you can also say that this is somewhat similar to the equivalence ratio, because in case of your equivalence ratio, the phi equal to 1 corresponds to the stoichiometric mixture. When phi greater than 1, we talk about rich mixture. So, it is something like phi minus 1 approximately. So, you can again see when there is no dissociation, this is the highest temperature. However, with the presence of dissociation, there is a change of about in the range of something like 300 to 400 Kelvin reduction in the final cycle temperature. Corresponding reduction will be in the cycle pressure as well, and therefore, we can lose in the cycle efficiency and output point of view. Final effect is the variation in the number of molecules. Now, you may be wondering what can be the effect of the number of molecules. Now, the effect comes from the ideal gas equation of state. Just think about the ideal gas equation says that PV equal to mRT, or you can also write as N R bar T, where N is the number of molecules, R bar is the universal gas constant. Therefore, you can write P is equal to N into R bar upon V into T. Now, for a given volume and temperature, then R bar being an universal constant, P is directly proportional to the number of molecules that is present there or number of moles that is present there, and therefore, if the number of moles increases, the pressure will increase. If number of moles decreases, the pressure will decrease, thereby affecting the work output. Think about some standard chemical reaction, like if we talk about say CH4 plus 2O2 giving CO2 plus 2H2O, the one that we just considered earlier. Now, on the reactant side, how many number of moles you have? 1 plus 2 equal to 3 moles. On the product side, 1 plus 2 equal to 3 moles. So, because of the reaction, there is no change in the number of molecules, they are in balance. Now, take another even simpler reaction, C plus O2 giving you CO2. Now, how many number of moles you can have on the reactant side? 1 plus 1 equal to 2, whereas we have only 1 on this side. Another common example, H2H2 plus O2 giving you 2H2O. So, on the reactant side we have 2 plus 1, that is 3, on this side we have 2. So, because of this chemical reaction, what is happening? Number of moles on the product side, that is actually reducing, and this thing is called, as the number of moles are reducing, this thing is called molecular contraction. That is because of the chemical reaction, number of moles are reducing, or total volume or total mass you can say is getting contracted a bit. I should not say mass, in mole sense, that is getting contracted, and as it is reducing number of moles, corresponding pressure also will reduce. A typical example with from other way around, we take C8H18. So, to have complete combustion of this plus O2, what we can have? We shall be having 8 CO2 plus 9 H2O. So, how many moles of oxygen will be required then? We shall be having 8 plus, so we can write it to be 12.5. Then how many moles we have on the product side? We have 1 plus 12.5, that is 13.5 moles. On the product side we have 8 plus 9, that is 17. So, number of moles are increasing in this case. There are more number of moles produced because of the chemical reaction, and this is an example of molecular expansion. Number of moles has increased, accordingly pressure inside the cylinder also is going to increase. So, because of this variation in the number of molecules, the system pressure can directly change, thereby affecting the total output. So, these are the 4 factors that can primarily affect the performance of engines, ideal cycles, and these are the 4 factors that we take into account in case of fuel air cycles. So, if we combine their effect, primarily effect of or if we just take a summarized effect, we have of course discussed each of them separately, but the effect of dissociation and the effect of variation in specific heat with temperature is more or less the same, to reduce the peak pressure and temperature of the cycle and thereby to reduce the net work output of the cycle. The effect of variation in the number of molecules is to affect the system pressure, whereas the change in the gas composition can affect the chemical properties of this. I would like to end today with a small numerical exercise. Here just read the question: what will be the effect on the efficiency of an Otto cycle having a compression ratio of 8 if CV increases by 1.6% during operation, K equal to 1.4, that is given. Only the variation of specific heat that we have to consider, or variation of K with CV that we have to consider to get the cycle efficiency. Now, for Otto cycle we know that eta equal to 1 minus 1 by r to the power k minus 1. Here it is given that r equal to 8, k equal to 1.4. So, if you put it there, then its efficiency under ideal condition, if there is no variation in specific heat, this should be 0.565 or 56.5%. But there is a variation in CV. So, how to take care of that? We know that k is equal to Cp upon Cv, that is k minus 1 is equal to Cp minus Cv upon Cv, and Cp minus Cv is equal to R upon Cv. So, eta can be written as 1 minus 1 by R to the power upon Cv, or 1 minus R to the power minus R upon Cv, or 1 minus eta. We are just trying to relate this eta with Cv, because these are the informations given to you. That is why we have modified k in terms of Cv, and we know capital R is a constant, small r is also a constant. So, 1 minus eta will become then R to the power minus capital R upon Cv, or we are taking a log on both sides to simplify this, minus log of r. Now, we are differentiating both sides. If we differentiate both sides, then what we are going to get? Going to have minus of d eta upon 1 minus eta, because log of 1 minus eta we are differentiating, that gives 1 minus eta, and then from that we have minus eta, minus of d eta rather. And in this side, which term is variable? CV is the only variable, because both capital R and small r are constants. So, from there we have CV to the power minus 1. So, we can say it is plus r into CV to the power minus 2, that is CV square, to log of small r to d of CV, or if we write d eta upon eta, taking everything on this side, what we can have is r upon CV into ln r into, we are writing as 1 minus eta upon eta. Okay, and r minus CV, from here it is k minus 1. Okay, sorry, I have dCV upon CV. I have broken this to CV square into two parts. So, r upon CV, this term is k minus 1. So, if we combine this, we have k minus 1 into 1 minus eta upon eta log of r into dCV upon CV. Now, what is given here? It is given that CV increases by 1.6% and I have a minus sign also. Okay. So, this CV increases by 1.6% means this dCV upon CV is this 1.6%, or we can say 0.016. We already have k, we have small r, and eta we have calculated as 0.565. If you put everything, then you are going to get this to be minus 1.025%. That is, only 1.6% variation in the specific heat during the operation causes more than 1% reduction in the final thermal efficiency. This is again only considering the effect of specific heat, a very simple analysis just to show how the variation in specific heat can affect the cycle performance. We shall be solving a couple more similar problems in the next lecture, and then we shall be talking about those losses which we have not considered in fuel air cycle and also the valve timing diagram. So, just to summarize today's observation, we have discussed about the limitations of air standard assumptions, practical factors which we are excluding here. Then the fuel air cycle was introduced, and 4 factors which comprises the fuel air cycle: the effect of composition of cylinder gases, effect of temperature dependence of specific heat, effect of dissociation, and the effect of variation in number of molecules have been discussed. So, on this fuel air cycle we shall be adding the actual cycle effects on also the valve timing diagram in the next lecture. Till then, you please revise this lecture, and if you have any query, please write to me. Thank you.